Welcome to the sixth episode of the Introduction to Assembly Programming using the 6502. In this episode, we're going to be talking about the stack. This isn't going to go into huge detail about what a stack is. It'll give a brief introduction like everything else. I'm not covering a huge amount of information here, but probably just enough to get started or ask questions. We'll also cover some of the stack manipulation instructions in the 6502. So let's get started. Before we talk about the stack specifically, let's talk about some of the address mapping in the 6502. We kind of haven't discussed this in the series to date, but the 6502 does have a certain address map of where certain things are located. And kind of kept that hidden so far from everybody, but let's talk about it here. So the 6502 has a single addressable memory space, meaning that a given value, address value, won't exist in two different memory spaces. So the ROM won't have address 0 and the RAM won't have address 0. I said at the beginning in the computer architecture I wouldn't go into the different architectures. There's von Neumann and Harvard architectures, or Princeton and Harvard, whatever you want to call them. On this device, all we need to know is that there's a unique address for everything that is addressable, and the 6502 has certain sections that are designated with special functionality. These can differ from device to device, and some devices might have different amounts of ROM or RAM. So I give an example of one 6502 core, the Ricoh 2A03. I believe this is the one that's used in the NES. But there are other 6502 implementations out there that have different address maps or different sizes for these things. But a lot of what I'll discuss here is the same. So the first memory range that we're going to talk about is the 0 page. The 0 page RAM is address 0 through FF, and they call it the 0 page because this bit, which would be the page bit, is these bits, which would be the page bits, is a 0. And why that matters, my dog wants to say hello. Why that matters is that some of the instructions can be more optimized. They use 2 instructions instead of 3 instructions for some of the 0 page RAM. Not really important unless you're trying to squeeze, the littlest bit of memory out of the device, or if you are disassembling, then it is useful to know the difference between the 0 page and the non-0 page instructions. But that's about it. The chunk of memory that's important for us today is the stack. The stack is located, it's a chunk of RAM that's located between 100 and 1FF hex. That's here. And then there's additional RAM that's after the stack, and that's from 200 hex to 7FF hex, depending on the device. And that's for any additional values that don't, or variables that don't fit in the 0 page RAM. Starting from address 8000 hex and onward is the ROM of the device. So this is the program code that's going to run when the device runs. And then we have a couple of special addresses that we aren't really going to cover in this class in too much detail. There's a interrupt vector, a reset vector, and an IRQ break location. And those are kind of beyond the scope of this introductory class. So the one we'll focus today in this session is mainly about this range 100 through 1FF, the stack. So what is a stack? A stack is like a stack of blocks or books. It's exactly that, which is why it gets its name. To get to the first thing in a stack, you have to remove everything you put on top. So if you put a book on the table, and then you put another book in the stack, and then you put another book in the stack, to get to the bottom book, you're going to have to take off the top book and then the next book, and then you get back to the bottom book. I guess you could, in theory, lift up the entire stack and pull that thing out. But logically, when you stack things up, we're going to pretend that they're too heavy to lift all of them up, and you have to, again, remove the things one by one to get back to the first one. This is also called first in, last out, which is the kind of opposite of the first in, first out. People have heard more of a FIFO than the FILO. But yeah, stack is a first in, last out. So kind of visualizing that example that I said. We put a book down on the table. We got The Hobbit here. We're going to stick another book, Firefly Lane, up on top. War and Peace. Maybe you can't lift that one with other books. On top, Timmy Failure, another book on top. We have a diverse set of reading literature here. But if we wanted to get back down to The Hobbit, we would first need to take off Timmy Failure, take off War and Peace, take off Firefly Lane, and then we're back at The Hobbit. So that's kind of how stacks work. They grow up in one direction and then they kind of decay back in the same direction. So with the abstract idea out of the way, let's talk about how this is implemented in the 6502. So we talked about the 6502 using addresses 100 through 1FF for the stack. So by default, the hardware has the top of the stack pointer. Remember, we talked about the stack pointer as being one of those special registers. Well, the stack pointer has really 1 byte worth of data down here, and a second phantom byte that's kind of hard-coded. And on some devices this might be different, but for the 2A03 device, this is hard-coded to 1. And on reset, the device puts the SP register, which is this bottom half, to FF. And so this entire thing together points to 1FF, the very last address in that stack RAM range that we talked about. All right, so I highlighted those. The first instruction that manipulates the stack is the PHA instruction, and that's a push the accumulator register to the stack. So here over to the left we have the PHA instruction. That's what that would look like. And over here we have the accumulator with a value of 5A over here. You can see in our stack RAM it's all zeros right now, and our stack pointer is pointing to 1FF. So when we execute this PHA, what it's going to do is the ALU is going to look at where the stack pointer is pointing, which is 1FF, and then it's going to copy the value of A into that location. So 5A got copied into where the stack pointer is pointing. But not only that, the next thing it's going to do is automatically decrement the stack pointer value. So now the stack pointer points to the next location that can be used. And that's important, right? Because then we could do another PHA and we can kind of stack those books or values on top of each other. The PHA register the PHA instruction doesn't affect any of the status registers. So none of those bits get set on that operation. So we talked about pushing a value to the stack. Let's talk about pulling one of those values off. So like in that example we saw at the beginning, we stacked up the books. Well, what if we want to take one of those books off? How do we do that? So we do that with the PLA instruction, and that's pull the accumulator register from the stack. And in this example, we are starting from a similar point that we were before. The stack pointer is pointing to 1FE, and we have our prior value that we wrote into the stack, 5A, still sitting there happily. The accumulator value has changed, though, probably as a result of some other operations that you were doing that caused you to want to save your previous A value, and now you want to get that back. So what's going to happen, this is wrong over here. This should say PLA. We'll issue a PLA instruction. I fixed it. And the first thing that the device will do is that it'll increment the stack pointer. And that will move the stack pointer back to 1FF. And then the second thing this instruction will do is read the value here at 1FF, where the stack pointer is now pointing to, and load that into A. So we get our 5A back from the stack. Now the stack pointer will stay pointing to 1FF because since we read out 1FF, it's actually empty, even though it still has 5A in it. It's the next location in the stack that can be written to. It's the place where we can stack the next value. So that's where it sits. So you can see when you stack something on, you stack it and then move the pointer. And then when you pull something off, you move the pointer and then take out the value that was there. So that's kind of the basics of how the stack works. For the PLA instruction, it does affect some of the status bits, the N and Z, so you can kind of get some information regarding the value that you pulled out of the stack. Okay, some of these instructions are getting a little bit obscure, but they should be fairly easy to understand if you followed along so far. The PLA, PHA instructions are used a little bit, especially if you're just running out of resources. You used X and Y index registers already, you have a value in A, you need to do some other operation. The stack can be a quick way to store A off and then pull it back. And so you'll see that sometimes. These next instructions are used less frequently, even less frequently, but all of these stack manipulation instructions aren't terribly common, but you see them a little bit. Where it is important to understand the stack is what comes next, the section that comes next, and that'll be subroutines, because the stack is heavily used in subroutines. All right, so PHP. What is the PHP? It's push the processor status register to the stack. So instead of the accumulator over here, we have the status register, with the N bit, Z bit, carry bit, V bit, all those, whatever. All the status bits, pushes it to the stack. This again doesn't affect any of the status registers itself. And then we have the opposite instruction, the PLP. Man, I did not do a good job of updating these instructions over here. Sorry about that. The PLP pulls the processor status back from the stack. So it takes the value from the stack and puts it back into the status register. This is also wrong. Since you're writing directly to the status register, it affects every single one of these bits. So, sorry about the error there. Yeah. In this instruction, you're reading the value from the stack and writing to the status register, so it literally changes every bit in the status register, except 1, which is always 1. So, all right. That's kind of the basics of the stack. If you didn't understand that, you're probably okay. Just keep going. And if you have issues in the subroutine section where we talk about how the stack is being used, you can come back here and watch this again. But maybe the subroutine section that's next will help solidify some of the ideas of the stack and its usage. Because, like I mentioned, the instructions, the PHA, PLA instructions are used a little bit, but not terribly common. All right, so next is basic subroutine and jumps. And this is a huge part of understanding assembly level programming. Very important for understanding the flow control and how to do a lot of things in assembly. So this is kind of the real chunk of what you need to know. All right. Hope you enjoyed. Have a great day.